Emeritus or Distinguished Professor at the State University of New York in Stony Brook. I know Jim since I was a graduate student. He was supposed to be on my PhD committee, but I think the week I made my defense, he left, went somewhere, so they had to put somebody else to replace him. But basically, with Prakash, it was there for my PhD work, and then we've been working together several times and have a bunch of paper about thermal evolution of neutron stars since 2000 until recently. And basically, Jim has been doing a lot of work on neutron stars. And he started, I think, with David Schramm. No? He actually predicted that neutron star merger would produce R process elements, something that was confirmed recently from the gravitational wave detection and the gamma ray burst in 2017. And he had an enormous amount of work on precisely the equation of state of neutron stars at low temperature, at high temperature for supernovae, neutron emission, and well, I probably forget 90% of his work, but it's a very impressive collection of work. And so today he is going to present us an overview of what we have learned about the equation of state and the mass and radius of the neutron star. So go ahead.
Okay.
Oh, what about questions? Do you prefer people to ask you questions during the talk or wait at the end?
If people want to interrupt at any time, that's fine.
Okay.
Let's see. Yeah, here we go. Yeah, please feel free to just burst in and ask whatever you would like, and then we have time at the end also to talk as well. But thank you for the invitation. I would like to be there in person, but that's a little difficult these days. And Danny and I have been working together for some time, as he said, and I've enjoyed the experience. And I wanted to talk today about the latest measurements of neutron stars and the implications for dense matter. I did want to acknowledge some generous funding I've received over the years, and also acknowledge, including Danny and others at UNAM, other collaborators that I've worked with over the last few years. The main topics I'd like to address are how neutron stars are related to the equation of state, what we can learn by focusing on the maximum mass of neutron stars, observational evidence for a maximum mass, and the role that causality plays in constraining the equation of state and constraining the properties of neutron stars. There's also been enormous progress over the years in nuclear physics and both theoretical and experimental aspects. There's even some connections with condensed matter physics through the unitary gas paradigm that I will look at briefly as well. And these offer extremely important constraints that are complementary to the astrophysical constraints that we can deduce from radio and X-ray observations. NICER this week at the APS meeting, maybe it was, yeah, this week at the APS meeting, announced some new results for the second neutron star that they've been investigating. And so I will have a brief summary of those, of the latest results from there. But for me, I think the most exciting development over the last few decades has been gravitational wave observations, especially of GW 170817, the neutron star merger. And that's just a glimpse, is giving us a glimpse of how these events going forward in the future are going to be able to constrain neutron star properties even further. So with credit to Danny, who drew this original figure probably 20 years ago now, It shows the major aspects of a neutron star, and the center, of course, has a question mark. So despite all the progress we've made in understanding neutron stars and measuring them and so forth, it's still a complete mystery what the inner core of a neutron star actually consists of. The 5 major regions of the neutron star are illustrated here. I don't know if you can see the cursor, but ranging from the atmosphere on the very outside, just a few centimeters thick, that determines what the X-ray spectrum. Neutron stars that we can observe typically have surface temperatures of a few 100,000 to 1,000,000 degrees. So the primary emission is in the form of X-rays. Underneath the atmosphere, we have a meters thick envelope. And depending on whether this envelope is primarily composed of heavy elements or light elements, that will affect the overall flux of X-rays from the atmosphere by about factors of 3 or so. So it's an important but unknown quantity that we have to infer from the observations. Below that, we have the real neutron star beginning, the crust, which consists of heavy nuclei, which in the outer portions are more or less ordinary nuclei, and then above densities of a few times 10 to the 11th grams per cubic centimeter, neutron drip occurs, so we have neutrons outside. It's believed that at least after a neutron star becomes a few hundred years old, that the temperature has decreased sufficiently, passing below the critical temperature of a superfluid for those neutrons, so that neutron fluid is actually largely superfluid in most neutron stars. At higher densities, the nuclei can deform as they become closer together, and the Coulomb energy becomes less important, and the structures can change to 2-dimensional or even 1-dimensional plates, and the matter can even turn inside out. So we call this transition between the crust and the outer core, where the matter has the nuclear structure completely disappears, and we have a uniform fluid of nucleons, neutrons, and protons. These transitions are basically, we refer to them as pasta phases, because of the analogy that these would be meatballs and spaghetti and lasagna. Danny actually likes to call these inside-out bubble phases Swiss cheese phases. But in any case, there's a definite food analogy there. And so the transition between the crust and the outer core is interesting, to say the least. The outer core, we think we understand reasonably well as being a fluid dominated by neutrons and protons. And the protons are probably become superfluid at an early stage, and the neutrons later on, after hundreds of years, can also become superfluid. And then the inner core, we don't know. Is there a population of quarks or quarkionic matter, Bose condensate, heavy nucleons, hyperons, strange particles? So we're going to have to rely, I think, on thermal observations of neutron stars to give us more insight as to the properties of the inner core. It's going to be difficult to entangle those properties just from measurements of the surface of the star itself. I won't have time to talk about all the very interesting superfluid aspects, both in the crust of the star and in the outer core, or the pulsar mechanism, the magnetic field structure, and so forth. One interesting thing that NICER has done, the Neutron Star Interior Composition Explorer, the X-ray satellite that's attached to the space station, is that for the first time we're able to map the magnetic field geometry of the surface, which going forward is going to be very interesting. The field distribution is much more complex than anybody has been modeling. That's the first thing we learn, is that any models that we've been using so far for the surface structure, for the surface distribution of the field are wrong. It's much more complex. And part of the problem with interpreting nicer results is that the complexity of that field, which is unknown, has probably got more than just a few free parameters that would be useful in modeling it. So given that complexity, the further progress in understanding these surface fields is going to be a challenge. But NICER's been only getting these X-rays for a few years. There are future plans for better and more powerful X-ray satellites in the future. So I think the path going forward will be focused on neutron stars in that way. So the connection between the equation of state and neutron stars is pretty straightforward. The general relativistic structure equations discovered in the early part of the 20th century, called the Tolman-Oppenheimer-Volkoff equations, relate, as in Newtonian gravity, the pressure gradient to gravity, and the definition of the mass is just the volume integral of a mass density. In general relativity, the mass also has internal energy contributing to the mass, so it's the total energy density. And for the pressure gradient, we also have contributions from the energy density as well as the pressure on the right hand side. So, but the only aspects of the equation of state that are important are pressure and energy density. The composition doesn't matter, at least at low temperatures. The temperature is just unimportant because it is so low. The matter is degenerate. The only aspects of the equation of state that enter these equations are the pressure and the energy density. And if you have a relationship between pressure and energy density that we call the equation of state, then integrating these equations from a central value, for example, suppose the central pressure is this value, the central energy density is this value, which is about 3 times the saturation density. So the scale down here is energy density in units of the saturation density. Scale on the side is using pressure in nuclear units of MeV per cubic Fermi on a log scale. If we integrate from this pressure and energy density at the center to the surface of the star where the pressure vanishes, then that will produce a configuration with this total mass, about 1 solar mass, and a radius of maybe 12 or 13 kilometers. And as we vary that central pressure, increasing or decreasing, we get either larger or smaller masses, and the radius adjusts as well. And the resulting mass radius curve is shown on the right. And the two most interesting properties of this overall curve are, first of all, that there's a relatively small range of radii for a given equation of state. As we increase the mass, the radius isn't changing much as we go from, say, 1 to nearly 2 solar masses. And secondly, a general relativistic effect that the mass reaches a maximum value. If you try to pile more mass onto the star, you can't. The pressure simply can't support the configuration and it will collapse. So there's a maximum central pressure that is possible for a neutron star that corresponds to this maximum mass. So the two aspects of a neutron star, at least simplistically speaking, that constrain most importantly the equation of state are the value of this maximum mass and the value of this radius. Now, I've only drawn this for one equation of state, and I get a characteristic radius here that's 12 or 13 kilometers. But if I were to do this for different theoretical models of the equation of state, that characteristic radius could be 11 kilometers or even smaller. And here, these models have characteristic radii of 15 kilometers.
Excuse me, James?
So there's always been this problem that although the radii for neutron stars are probably not changing much with mass, we don't know precisely what that radius is. We have made progress. The maximum masses of these different equations of state, you see, range from 1.4 to almost 3 solar masses. We have made considerable progress in being able to constrain things on the maximum from a maximum mass perspective. We observe pulsars with masses of 2 solar masses or possibly even larger. So that basically rules out models that can't produce stars with that mass. And so this is interesting that one of the major pieces of progress over the last 20 years or so has been the increase of the estimated maximum mass from about 1.4 to 2 solar masses or even larger. And so this has focused the equation of state work considerably and ruled out a number of models for the pressure energy density relation above a few times the saturation density. So this figure summarizes then in the mass radius plane, the theoretical mass radius curves. We hope that we could measure simultaneously the mass and radius for several objects and be able to pick out which of these curves or a different curve, and then translate that by inverting the structure equations and obtain the pressure as a function of energy density. These different regions here in the upper left are ruled out. The event horizon of a black hole would basically prevent the radius of an object from becoming smaller than 2 times gm over c squared. That rules out this blue region. The light blue region is ruled out by the requirement that the pressure has to remain finite in the neutron star. And then, assuming that the equation of state is causal everywhere, rules out this larger green area. And causality plus the observed maximum mass minimum of 2 solar masses rules out this additional slice here. All these equations of state satisfy these different constraints. On the other hand, we have a constraint for large radii that's basically based on the fact that we do observe neutron stars that are spinning with millisecond periods or close to a millisecond period. The most rapidly rotating star has a frequency of 700 hertz. And mass shedding from the equator would occur for a uniformly rotating object of a given mass if the radius exceeds, when the radius of the non-rotating star exceeds this green-gray boundary. And there are selection effects in picking out high-frequency pulsars, but going forward with the SKA array and so forth, we hope that we will be able to push the large radius constraint from the point of view of rotation even further than this pulsar has been able to do. The final thing I wanted to point out from this slide is this concept of a radiation radius and a redshifted radius. If we observe thermal emission from a neutron star and can get an estimate of the total flux of the object and the temperature of the object, then Kirchhoff's laws will tell us, give us an estimate then of the radiating surface area. And because both the flux and the temperature are redshifted, the inferred area that we observe is also redshifted. So in fact, thermal observations don't give us a precise radius, but they give us a functional radius as a function of mass that would follow these different orange curves. So we're measuring here R infinity of 10 or 12, 14. We get these, we'll get a band of an uncertainty region that will follow these orange curves rather than a strict radius itself. Prakash and I discovered about 20 years ago that there is a close connection between the pressure of matter near the saturation density. Move this. And that as you explore stars going from small radii, 9 kilometers to 15 or even 16 kilometers, these acronyms here are for different theoretical equations of state. If we look at 1.4 solar mass stars, we find that the radius times the pressure of matter at particular densities, like twice the saturation density or 1.5 times the saturation density or 1 times the saturation density, they're correlated by about the 1/4 power of the pressure time inverse 1/4 power of the pressure times the radius. So if we look at the pressure of these different equations of state at 1.5 times the saturation density, and take the pressure to the -1/4 power and multiply it by the radii predicted for 1.4 solar mass stars for these different equations of state, we find that the product has a relatively small scatter. So what this means is that the radii of ordinary neutron stars is therefore highly correlated with the pressure of matter in the vicinity of the nuclear saturation density. And since this time, many other correlations called semi-universal or universal relations that are independent of the equation of state have been established. And this is sort of the first one that came to light. And so this is the first and most fundamental connection then between the equation of state and neutron star structure, is that if we have a good handle, perhaps from nuclear physics experiments, what the pressure of matter is around the saturation density, we can predict what the radii of ordinary neutron stars are. And vice versa, if we can measure that radius with precision, we can determine the pressure of matter around the saturation density. So we can approach the problem from both ends, as we will see. So the reason that the radius and the pressure are connected is a result of the TOV integrations. And so the question is, what determines the pressure of matter near the saturation density? And that turns out to be what's called the nuclear symmetry energy. Basically, the symmetry energy is the difference between the energies of pure neutron matter and symmetric matter. So pure neutron matter has a proton fraction of 0. Symmetric matter has a proton fraction of 1/2. And the symmetry energy is basically, at a given density, the difference of energies of those two configurations. So this sketchy figure basically illustrates for a number of different equations of state how the energy per baryon changes with density in units of the saturation density. Reach a minimum of -16 MeV, the bulk binding energy inside of a nucleus. And then that increases, the energy increases as we go to higher densities. But if you look then at the corresponding energy of pure neutron matter at the same density, instead of -16 MeV, it's more like +14 or 15 MeV. And the difference between -16 and 15, or about 31 MeV, is what we call the symmetry energy. And so one parameter you can establish is what the symmetry energy is at the nuclear saturation density. We call that SV. It's about 31 MeV. We can also look at the slope of this curve, the derivative of the energy with respect to the density. And that's the so-called L parameter. So basically what we can do is both expand this energy in terms of density and in terms of proton fraction. And so the first item that's important is that if we expand in terms of proton fraction at any density, symmetry tells us that the leading order term will be quadratic, because the minimum of the energy is always where you have equal numbers of neutrons and protons. And so that means that the leading order term in an expansion in symmetry is going to be quadratic. And surprisingly, it turns out that this expansion, the next order term will be quartic and will basically have a very small coefficient. So it turns out that a very good approximation that will connect matter from any proton fraction, including pure neutrons at x equals 0, to that at 1/2, can be described by simply this quadratic term, this dependence. So that means that the important quantity then is this coefficient then of the quadratic term, which we call S2. And S2 as a function of density can be expanded around the saturation density in terms of the slope in terms of the value of the symmetry energy, the difference of these two curves, and the slope of this curve, because the slope of this curve here is 0. And so SV and L then are the two are the leading order terms, the 0th and first order term in a density expansion around the saturation density. And since we can use this formula to describe pure neutron matter, you can see for pure neutron matter, X is 0. So the difference of neutron matter, energy, and symmetric matter is simply SV. And the pressure, which is related to the derivative of the energy, is simply going to be related to the L parameter. So SV and L correspond basically to the energy and pressure, within constants of pure neutron matter. And of course, pure neutron matter is not exactly what we have inside of a neutron star. In the important outer core, the equation of state is determined by beta equilibrium, actually in the entire star. The proton fraction at any point is determined by energy minimization. You take the energy of the baryons, the energy of the electrons or fermions, all of which are fermions, and vary that with respect to the proton fraction to optimize the proton fraction. The optimum proton fraction, here called X beta, turns out to be very small, just a few percent. And so that the pressure is actually very close to the pressure of neutron matter, because the proton fraction introduces, the finite proton fraction is very small, and you get a very small correction of the order of a few percent. So for all practical purposes, the energy and pressure of matter around the saturation density are determined by these nuclear parameters, symmetry energy parameters, SV and L. And since the radii of stars is determined by the pressure of matter near the saturation density, you can see that there's a direct connection now between this L parameter and the radii of neutron stars. A weaker connection exists with the symmetry energy itself, but dominantly the closest connection is through this L parameter. So that is basically the connection then between the nuclear physics and the astrophysics. There's been very important progress made in understanding the properties of neutron matter in recent years from a theoretical perspective. In fact, the only known way of calculating this in a progressively perturbative way, which allows you to make estimates, realistic estimates of the error, of the uncertainty in your approach, is this chiral expansion techniques that have been developed. And basically it provides the only consistent framework that we know of for estimating the uncertainties as a function of density. So this figure on the right, for example, shows the predicted neutron matter energy as a function of density. Here's nuclear saturation density around 0.16. This goes up to about twice saturation density. The uncertainties with increasing density, but at least up to densities of the nuclear saturation density and perhaps a little bit beyond, the theoretical estimates of neutron matter seem to be under pretty good control with relatively small errors. The figure on the left shows the corresponding pressure obtained from this energy curve, again with 1 and 2 sigma uncertainties in this approach. I'll describe the unitary gas limits I think in the next slide. But this is important progress that's been made over the last decade, is firming up theoretically from more of a first principle approach, many body approach, how the energy of interacting neutrons behaves. These calculations are constrained by many body calculations of light nuclei, which basically give us some information about the 3-body and higher order interactions among the nucleons. These expansions break down when we get beyond about twice the saturation density, but at least we have a basis on which to develop. properties of matter at higher densities, building upon this approach. So the unitary gas is a theoretical concept which can be actually experimentally created in cold atom experiments. Technically, a unitary gas is a collection of fermions that are interacting primarily through short-range S-wave interactions with the properties that the scattering length of those interactions are infinite and at the same time have zero range. And you can tune cold atom experiments for argon, for example, to have the same properties of range and scattering length. And what you find from a theoretical perspective, then such a gas basically has only one scale in it, which is basically the Fermi wavelength, which is a function of the density. And theoretically, one can predict that the energy should be proportional then to the Fermi energy. And experimentally, one can confirm the theoretical predictions, and you find that this so-called Birch parameter is the constant that relates the energy of this theoretical unitary gas to the actual observed energy, which is proportional to the the Fermi energy of a degenerate fermion gas at the same density. That Fermi energy varies as the density, as the wave number squared, or as the density to the 2/3 power. So using this value for the Birch parameter measured in these cold atom experiments, we have a prediction for the energy of a unitary gas that behaves very simply as density to the 2/3. Now, it turns out that a neutron matter gas is not a unitary gas because the interactions don't have infinite scattering length and they don't have zero range. However, the scattering length is very large and the range is actually quite small. So the unitary gas is a first approximation, so to speak, for neutron matter. And it turns out that if you tune the cold atom experiments to have a finite scattering length and finite range, the energies of such a gas increase. In addition, neutron matter also has 3 body terms. So there are additional interaction terms beyond S-wave interactions. But more or less, almost all of those extra kinds of interactions from multi-body terms or from higher order waves are repulsive. So they also increase the energy from a unitary gas. So an absolute minimum, according to this unitary gas conjecture, is that an absolute minimum to the energy of neutron matter, and therefore, roughly speaking, neutron star matter, is going to be given by this simple expression. And if that turns out to be the case, you can then place constraints on the L parameter as a function of SV. And it basically rules out this whole gray region and allows this green region. And an equation of state that I developed with Doug Swesty back in 1991 and has been often used for supernova and neutron star merger simulations, turns out to have symmetry parameters that are in violation of this constraint. And ideally, this equation of state should be recalculated with different symmetry energy parameters. And it turns out that many other ones, this is the Shen equation of state, also violates the unitary gas constraint. However, there are several other modern interactions that do satisfy the unitary gas constraint, and these shaded regions are calculations of neutron matter, which also satisfy the unitary gas constraint. So this theoretical constraint supports the theoretical neutron matter calculations that have been performed. In addition, the most important observable that we have when we look at nuclei are their energies, their binding energies. And because of competition between the volume and the surface, that basically gives us a systematic relation between these two aspects in terms of sort of a liquid drop approach to nuclei that can be translated into a correlation between the L and SV parameters that has to be maintained in order to fit the properties of both light and heavy nuclei. And that's a very powerful constraint. You can't pin down the value of L or the value of SV individually, but you do obtain a correlation between the two parameters, which has around a 97% degree of correlation. And so this is the most powerful piece of information that we get from nuclear structure as to the properties of the symmetry parameters. For comparison, the boundary from the unitary gas constraint is shown here. So predominantly, the most favored regions for the L and SV parameters from studying nuclei are satisfying the unitary gas conjecture and predict that L is around 40 or 50 MeV and SV is around 30 or 31 MeV. We can play the same game by looking at the correlations involved between the symmetry parameter and L for neutron matter. So this is the result of N3LO calculations of pure neutron matter using the Cairo-Lagrangian expansion approach. You get a similar correlation to what you expect from fitting nuclei. This is completely independent of any fits to nuclei, and it's simply based on the properties of neutron matter. And again, you get a similar prediction for the most favored L and SV values. The correlation has a slightly different slope than this one, and the correlation isn't quite as tight. But there's great deal of consistency then between the predictions from neutron matter and the predictions of nuclear structure. And very recently, the PREX-2 neutron skin measurement of lead-208 was their results were announced, and their result after years of accumulating data is that the neutron skin thickness, the mean square difference between the neutron and proton radii in lead, is around 0.28 Fermis with about a 25% uncertainty. And depending on how you model nuclei, there's a little bit of systematics here, and these two approaches basically summarize the main systematic differences that you might expect. But there's a very tight correlation between L and SV that can be obtained by looking at the neutron skin thickness in a heavy nucleus like lead. Both approaches end up giving roughly the same answer, and for a neutron skin thickness of 0.28 or so, what you find now is that the predicted L parameter from the PREX experiment is on the order of, in this case, about 100 MeV, and in this approach, which relies on relativistic, on skirm interactions. This one depends mostly on relativistic mean field interactions. Here we get an L parameter of about 120 MeV, which are quite large compared to what we expect from other nuclear experiments, where we get around 40 to 50 MeV. So at first glance, this seems inconsistent, but when you take into account that the neutron skin thickness measurement is only accurate at this time to about 25%, and you go down here to this is the 1 sigma bound, we find that in fact the present neutron skin measurement is consistent with a neutron skin thickness of about half of what was observed, and an L parameter of around 40 MeV in this case, and maybe 55 or 60 MeV for this case. So at about the 1 sigma level, as surprisingly large as this neutron skin measurement was, and the initial result that the predicted L parameter is very, very large, in excess of 100 MeV. In fact, at 1 sigma, this Prex experiment and other nuclear systematics are entirely consistent with each other. And this just illustrates the further progress that's going to have to be made with measurements of nuclear properties that are so small in order to get additional constraints on the properties of nuclei from the neutron skin thickness perspective. And if I take the neutron skin measurements with these two different systematic approaches and combine them with both the nuclear mass constraints and with the neutron matter constraints, this shows the 1 sigma, 2 sigma, and 3 sigma confidence bounds for the correlations between L and SV. And you can see that there's very little difference between the two ways of modeling the neutron skin. And the predicted value for L ends up being on the order of 50 MeV, with an uncertainty of only at the 1 sigma level of less than 10 MeV, and at the 2 sigma level it's about 12 MeV. So the overall result is that from nuclear physics perspective, these symmetry parameters, L and SV, are actually known at the present time with a pretty high degree of confidence. And now we would like to turn to astrophysics to see how well these symmetry parameters can be predicted from measurements of neutron stars, and to see whether there's actually any large inconsistencies that will have to be resolved. The short answer is no. So to connect then the nuclear physics results with the astrophysics, the first thing you can do is from a theoretical perspective, which is suppose we claimed we understood the properties of nuclear matter up to twice the saturation density, which is where these kinks occur. They predict mass radius bounds depending on the uncertainties in the neutron matter calculations, 1 and 2 sigma, that give these relatively broad bands going up here. And then above that density, you can, first of all, take a curve that will give you the maximum radius by basically saying above this density, we take the equation of state to be that where the speed of light is simply equal to, where the speed of sound is equal to the speed of light. You can't exceed that. This will give us the maximum possible radius for a given mass for the regions above this mass. And so that's these set of bounds. On the other hand, if you say that the maximum mass is 2 solar masses, then these sets of curves basically will represent the minimum radius as a function of mass that's possible. So this restricts the mass radius plane then to the region between the curve on the left and this gray curve on the right. If the maximum mass turned out to be 2.6 solar masses, for example, then you'd have to look between this red curve and this gray curve, which would in fact constrain the mass radius behavior to a very small amount. Another way of seeing this information is in this figure. This shows the radii range for 1.4 solar mass stars, depending on what you assume for the maximum neutron star mass. As you go from 2 to 2.3 to 2.6, we go from the blue to the green to the red curves, and you can see that small radii for 1.4 solar mass stars are being ruled out progressively. So I don't have time to explain these figures in more detail. You can look at this recent paper by Drischler et al. That explores the theoretical bounds that you can obtain from using neutron matter calculations up to various densities ranging from 1 to, in extreme case, up to 3 times the saturation density. So measuring neutron star properties, we've gotten a lot of information from pulsar timing. They can accurately measure masses. So most neutron stars have masses between 1.2 and 1.5 solar masses, and the lowest neutron star masses are around 1.1, and the highest are around 2.1. at least those with relatively small uncertainties. There are higher estimates, but they have relatively large uncertainties and shouldn't be counted on right now. X-ray observations can also yield radii, and so can gravitational wave measurements. So I'm running out of time here. I will say that the GW 170817 was an extremely important event because it gave us information on the radii through the so-called binary tidal deformability. The difference between a black hole merger and a neutron star merger is the role of tidal effects. Black holes basically don't have these tides, and tides will basically speed up the in spiral. So if you look at these purple curves compared to these blue curves, you see that the merger occurs at a shorter time, less time than the case where you don't have much tidal interactions. And the change in phase as a function of how the frequency of the gravitational waves, which is increasing as we move from left to right, is given by this simple formula in the lowest post-Newtonian approximation. And it's proportional to this so-called binary deformability, which is a function of the two deformabilities, lambda 1 and lambda 2 of the two stars. So the tidal deformability is basically the ratio of the induced dipole moment of the star to the external tidal field. We make it dimensionless by dividing by mass to the fifth. And in any case, the tidal deformability is this mass average of the two individual deformabilities. Let me skip ahead. You can show that the binary deformability basically times the divided by the radii of typical 1.4 solar mass neutron stars is largely independent of the masses of the stars in the emerging binary. This range here, here's GW 170817. There's very small uncertainty then in this number. And so this allows us to immediately infer the radii of 1.4 solar mass stars from this measured deformability. And even if the deformability is not measured very precisely, the radii only depend on its 1/6 power. So even a poor measurement of tidal deformability is going to give us a great deal of information. So here's the results from GW 170817. Depending on the mass ratio, the binary deformability here on the log scale, here's 100, here's 1,000. So the 1 sigma uncertainty is shown by the inner curves, the 3 sigma uncertainty is shown by the outer curves. So there's considerable uncertainty then in the measured binary deformability, but again, it's only the 1/6 power of that we're interested in. And so that leads to estimates then of the radii of neutron stars, the 1 sigma level, that go from say 9.5 to about 12 kilometers. And so that's, you see, is completely consistent with what we expected from the nuclear physics results. So at first glance, the gravitational wave measurements were completely consistent with the underlying measurements from nuclear structure. Interestingly, this gravitational wave event also allowed us to infer the upper limit to the maximum mass, and it turns out that if depending on the overall mass of the two stars in the binary, which is shown on the vertical axis, we have these 3 basic possibilities. If the masses of the two stars are really large, they merge and immediately go into a black hole. There's no gamma ray burst. If they're a more moderate level, you go into a short-lived hypermassive neutron star phase, which when it settles out into uniform rotation, collapses into a black hole, and you do get a gamma ray burst. And finally, if the two stars are relatively low mass, you form this hypermassive neutron star. It can settle into a supermassive neutron star that's uniformly rotating and survive for many hours or decades or centuries before collapsing possibly into a neutron star. And so we think the GW 170817 was an example of this intermediate case, because we did see a gamma ray burst, and we got mass ejection as well, producing a kilonova. And so that this bound here represents basically a property that can be connected to the maximum neutron star mass. Basically, the observed masses of the two stars in the binary combined had to be very close after you take out binding energy effects to the maximum neutron star mass. And so this gives us an estimate then that the maximum mass of a neutron star is very close to 2.2 solar masses. So the lower limit we have is 2 or 2.1 solar masses from pulsars. And now we have this estimate for an upper limit that's about 2.2 solar masses. So this would be really amazing if we ended up being able to constrain the maximum mass to such a high precision. So I'll finish off with just describing the NICER results that have been obtained to date. NICER basically measures the properties of a star by looking at pulse profile timing. Due to hotspots that might or might not be on the surface of the star, as they go in and out of our field of view as the star rotates, you'll get a periodic light curve. And depending on the compactness of the star, if the star is really compact, we can see around most of the other side of the star, and these pulsations will be relatively weak, the dashed dotted line here. On the other hand, if the star is not very compact, we don't see much of the other side of the star, and the pulsations will be relatively strong. That's this this dashed curve here, which has the biggest pulses. So hopefully from this we can get information about the masses and radii. From the measurement of the first neutron star whose results were announced, J0030, the two groups that analyzed this gave fairly consistent results with each other and predicted masses and radii that were in this range. The uncertainties are quite large, but pretty consistent with what we obtained from the gravitational wave measurements. And if you combine these NICER results together with the gravitational wave results, you find that at 1 sigma, that the radii of neutron stars is what you expect, again, from nuclear physics, somewhere between 11 and, say, 13 kilometers. Now, the latest results from NICER were announced this week at the APS meeting, and basically they look like this. There's a lot of systematics. You can take the NICER data alone and combine it, or combine it with XMM data for the pulse to interpret the pulses. And you can see that the addition of extra information from XMM actually tends to increase the uncertainties in the results. There's also a difference between the two groups that model this. These are from Miller et al. And these different sets of curves. NICER alone is shown in the blue. The NICER plus XMM is shown in the red. XMM by itself is shown in the gray. So what's interesting about this star is that it's got a mass of over 2 solar masses. And so looking at the differences between the radii of this star and the radii of the other star, which is around 1.4 solar masses, in principle can give us interesting information about the equation of state. Unfortunately, the uncertainties in these radii measurements are too large to make any comprehensive conclusions at this point. So this summarizes the radius interpretations from the different groups and the different ways in which the data is used, these different colors and different patterns. You can see there are roles played by the assumed underlying priors for the radius, which from the Amsterdam group was only up to 16 kilometers, but the Maryland group included as a prior radii to much larger values, which allowed these curves to extend to much higher radii and increase the estimated radius as a result. So there's still a lot of systematics depending on what data is included, how the modeling is done, what priors are assumed, and so on. So I think many, many more stars are going to have to be observed, and for conclusive results to come from these X-ray missions. But again, it's early days, and hopefully we will get better information as time goes on. So I'll just finish here by saying that the biggest tension that we seem to have between nuclear physics and astrophysics comes from these neutron skin thickness measurements, which are very difficult, and because the measurements are of very small distances in nuclei, a fraction of a Fermi, or compared to the overall size of the nucleus, which is about 7 or 8 Fermis. And but GW 170817 and NICER both give us radii in the range that we expect. We don't have precise enough numbers yet to pin down the particular equation properties of the equation of state, but we can feel comfortable that we're on the right track at this point. So I'm sorry I ran over a bit. I'll be happy to answer any questions at this point.
Thank you very much, James.
Okay.
Anyone have questions? Enrique, please.
Hi, James. Nice talk.
Yes. Hi, Enrique. How are you?
Nice to see you again.
It's good to see you.
Yeah. Yes, yes. So I have a couple of things that come to mind. So one of them is there's this very recent result, I think it might be from January, where there's a rather nearby, I think it's like 1,500 light years, 3 solar mass or 3.05 solar mass black hole. So how important is that? I guess it puts a definite upper bound to the maximum mass. But the other thing that kind of is in the back of my mind with all these new 2.0 and above solar mass neutron star is, did they accrete that extra mass? Did they form like that? Because mechanism would be rather different. In one, you are accreting mass, probably there's a high temperature on the surface, but the star is not too hot on the inside necessarily. Whereas if you form those 2 solar mass neutron stars in a core collapse supernova, you have a slightly different form. And how does that put limits to the equation of state? I mean, the fact that you have probably different temperatures for forming these objects.
Yeah. So first of all, with respect to low mass black holes, there's not only this observation you were talking about, but also some of the runs from the 03 LIGO run. In 2 cases, there were 2.5 or 2.2 solar mass objects that could equally well, that LIGO, I think, preferred to describe as neutron stars. They call them.
We don't know. Yes.
Right, but in fact, you can equally well model the gravitational wave signal by assuming that they are black holes and have no tidal effects. So the tidal effects are weak. First of all, because for such massive objects, of course, the tidal deformability becomes very small. So a high mass neutron star will behave like a black hole because it's pretty compact. And so there's absolutely no way to distinguish from gravitational wave measurements alone whether you're dealing with a high mass neutron star or a low mass black hole. So given the constraint from GW 170817, I myself prefer to believe that they have observed, under 2.5 solar mass neutron star black holes in one case, and maybe 2.6 solar mass in another case. This fits in with the 3 solar mass black hole that you described. So that in fact there's really no gap between neutron stars and black holes. But there's a definite maximum mass, and if you're above it, you become a black hole. Period. Now the question as to whether supernovae produce 2 solar mass black holes or whether those are a consequence of accretion, I think in practice it becomes very difficult to accrete more than a few tenths of a solar mass even over billions of years. lifetime of a neutron star. And I think the modelers prefer to think that high mass neutron stars may be the result of the relatively rare high mass supernovae. Of course, population, the saltpeter mass distribution favors very much low mass supernovae compared to high mass ones in terms of quantity. And so perhaps maybe once we get better statistics of the numbers of neutron stars of different masses, I suspect what we'll find is that high mass neutron stars are pretty rare. And
However,
this could be explained by the rarity of high mass supernovae.
right. But however, I mean, you already, well, we don't know the masses, but we already have like 2,000 plus known pulsars. And
Right.
I don't see any hints or too many hints of a continuous distribution between 1.4 to 2.1. There's more like small gaps or patches, probably because, as you mentioned, low statistics. But I don't know if that's...
Well, the high mass neutron stars we observe are the direct result of selection effects that the computer programs use to pick out systems for further study from radio timing. Favor looking for edge on systems with Shapiro time delays, which are which will be the ones in which, and if the mass is high, I think it's a selection effect to pick out the high mass neutron stars. So I think if we simply look at the neutron star masses that we've obtained so far, there's a big selection effect that's favoring high mass neutron stars. And so the fact that there are relatively few, even given that selection effect, means that in practice they're probably extremely rare. That's my own view.
Okay, thank you.
Right. So I think there are selection effects against observing high mass neutrons, against observing, in favor of finding high mass neutron stars. So, yes.
Yuri,
Yes,
please.
Yuri.
Hi, I have a question about the slide before the summary, the nicer results.
Okay.
So
This one?
yeah.
Or this one?
No, this one is fine. So about the radius, because one of the point of nicer was to reduce the uncertainty in the radius, right, to this famous 5%.
Yes.
So
yes, which I think is proving to be a overestimate of the
yeah,
an underestimate of the uncertainty, right? So
yeah,
I think that we're finding that this pulsar timing technique is going to need a lot more photon counts to reduce these uncertainties. And the biggest problem is simply the model. Extra parameters are the shapes of the spots, the number of spots. It's not just mass and radius and maybe interstellar absorption. We've now got a whole new set of parameters to fit.
Yeah, exactly.
With the same number of photons, we're not doing much better than for quiescent sources or photospheric radius expansion sources in terms of the uncertainties, unfortunately.
Yeah, I was thinking that the problem is indeed the shape. I mean, knowing the shape would remove a lot of uncertainties, right? Or having a better estimate of the uncertainty of the shapes. But the question was, how is there an explanation why combining the night? Because in the next slide, both nicer alone and XMM alone give basically radii that are the peak, for example, of the distribution are below 12 or 13, but combining them, they push each other forward. So is there an explanation why?
There is. I can't describe it simply, but I think in the papers, it describes why adding XMM is producing this effect, and it's a modeling difficulty.
Is it because it moves the mass, or?
No, the mass is they already are assuming the mass is constrained by the pulsar timing for this case.
Okay.
So the mass is not an independently derived quantity. It's already restricted to be between 2 and 2.14
Mhm.
solar masses by the timing. Okay.
Mhm.
If that mass constraint wasn't imposed, these radius curves would
Be much
greatly
bigger.
expand in terms of their
Mm.
uncertainty. So that's the only reason that they actually look like they're peaked here. If we didn't have the mass measurement
No, yeah,
to
yeah.
use as a constraint, the situation would look a lot worse. So yeah, the situation would look better if XMM wasn't there, but it's not fair to ignore that data either. So,
Yeah, no, I agree.
but you can see from XMM by itself that the radii are not very well constrained at all and can continue to extremely large radii.
Yes,
So,
yes. But I was saying that, for
and the two
example,
groups had different philosophies about what priors to assume for radii. The Amsterdam group said, okay, we know on the basis of nuclear physics and GW 170817 that 16 kilometers is an absolute upper limit. And the Maryland group decided we don't want to impose any constraints from nuclear physics at this point, and allowed the radii to go up to 22. And that I've questioned that approach. I thought they should be using the same priors, but it turns out that introduces about 0.3 to 0.5 kilometers uncertainty or difference in the final results. And the differences that are being observed when you include XMM are more like are at least double that. So that's not the major source of uncertainty here.
yeah, and also the
It's a
peaks are
model.
within the priors.
The two groups also make different assumptions about the range of inclinations that the system has, which again are not perfectly constrained by the pulsar timing. And so that that's another variable that
Yeah, and that affects the radius probably because it affects the shapes a lot. So
right. But those papers are now on the archive, and I think they do describe in some detail what adding XMM data is doing to the fitting.
all right.
But yeah, that is an uncomfortable result, but they didn't want, you can't hide it, so they're showing it. That's all.
No, it's fair. Okay, thank you.
Yeah. Okay. You're welcome.
Danny?
Hi, yeah. I have a question to start about this very massive neutron star, 2 solar mass above, because the measurements are all from the Shapiro effect. No? So
Yes.
Shapiro effect means we are almost in the equatorial, in the orbital plane, no? And when the white dwarf goes between the pulsar and us, we see a big effect, no? But the probability that we are in the orbital plane is very small. So there should be a lot of these heavy, massive neutron stars around, no? So has somebody tried to do statistical study of this, or what it means?
The trouble is the selection effect is huge. The algorithm picks out these systems that are edge on. So
yeah,
I think that there are tens of thousands. There are tens of thousands of other possible pulsars that haven't been analyzed, and not added to the database yet because it's just a big backlog, and they want to get data on the ones where they can actually say something. So, or that are at least interesting. So, yeah, I think the selection is favoring the discovery of high mass systems at this point.
Yeah, but also what I mean, the likelihood that we are in the orbital plane is very small, no?
Yes.
So we only think at the tip of the iceberg of that population. No? There are a lot of them that we.
That's already telling you there's a huge selection effect, right? It's just not right that out of the 2,000, we should be seeing 4 or 5 systems within a degree of being edge on. That's just statistically not allowed, right? If it was random. So it's already telling you there's a big selection effect going on.
From the detection, yeah.
From the detection algorithm.
Yeah.
Yeah. Yeah, no. If one thing is true, the inclination in the sky ought to be random. I mean, I don't see any reason to favor a certain inclination from exoplanets or from these systems. So.
Okay, good
Yeah.
point. Yeah. Okay, thank you.
Mhm.
I don't see more
I think you-
questions. Sorry.
Mhm. No, go ahead. Sorry.
No. You please. Because I don't see more questions in the chat or.
Okay.
Then, if there are not more questions, thank you again for accepting our invitation. It was a great talk, and thank you very much. Then we can.
Okay, you're welcome.
We can turn on our camera to say goodbye.
Okay.
Thank you very much, and see you next week.
Thank
Okay.
you.
Thanks.
All right. Goodbye. Thank you very much for the
Bye.
invitation. Bye.
Okay,
Bye.
thanks a lot, Jim.
You're welcome.
Thank you, Jim.
Bye, everybody. See you next week.
Bye.
Bye.